Hey folks, welcome to the video. Today we're going to be discussing the rate of change of functions, i.e. the derivative. We're also going to look at an example of the derivative from physics describing the velocity of a particle. Let's get into it. Calculus is the study of functions. And when we study functions, we often want to know what the rate of change of a function is. The quantity that describes the rate of change of a function is something we call the derivative. That's what this video is going to be about. Now, we study functions. These functions typically take in real values and output real values. So for example, some functions could be f of x is x squared, can be x cubed plus 1, could be cosine x, and so on. So it just takes in real values and outputs real values. Typically, we would want our functions here to be continuous. And if they are continuous, we can ask the question, how do these functions change in x? And to answer that question, we first look at this graphically. Let's say that this is x, and let's say that this graph here is the graph of f of x. And we're going to be concerned with some point here at x and at height f of x, and some point over here that's delta x away, so it's x plus delta x, and over here the height is f of x plus delta x. So those 2 points. And we would want to know what the rate of change of f is across these 2 points. Well, the rate of change of f across these 2 points is just the ratio of the change in f to the change in x. We write that as delta f over delta x. Over here, delta just means change in. So delta f over delta x is the change in f, which is f evaluated at x plus delta x minus f at x over the change in x, delta x. Now, this quantity describes the rate of change of f across these 2 points, but it's also the slope of this tangent line. The slope of this tangent line is delta f over delta x. Let's say we were to bring delta x in closer. If we were to reduce the size of delta x, reduce the distance between these 2 points. We keep x fixed, and let's say we were to talk about this new point here. Let's say that this was our new x plus delta x. Then this would be our new f at x plus delta x. And the slope of this line changes. So the slope of this line changes. It looks like in this case it has reduced. So the rate of change of f across these 2 points is different from the rate of change of f across the previous 2 points. If we were to bring in x plus delta x even closer to x, so reduce the size of delta x even further, now over here, then the slope changes once more as such, and we can keep doing this. We can keep doing this and bring it arbitrarily close to x. So say we were to bring it arbitrarily close to x, right there. Then this line that we see over here, let me use a different color. Whoops. Yeah, let's use a different color. will go green. So this line over here represents the tangent line to f at the point x. Okay, so what does this mean? As delta x goes to 0, the slope of the line changes. Moreover, the line gets closer and closer to being a line that touches only one point locally on this function f. Notice that initially the two blue points that we had started with, this one over here and this one over here, the line that connects those two hits f of x at 2 points. And as we keep bringing those 2 points closer and closer together, the line still hits 2 points of the graph of f. But if we were to bring x plus delta x arbitrarily close to x, if we were to take delta x to 0, then this tangent line hits the graph of f at only 1 point locally. So what's happening here? We're saying that the limit as delta x goes to 0 of delta f over delta x, which is the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. This quantity, it still represents the slope of a certain line, and we give this quantity a name. We define this quantity to be the derivative of f evaluated at x. So that's the derivative. The derivative is the slope of the tangent line of f at the point x. Okay, now let's understand how this works in practice. Let's suppose, so let's look at an example now. Example. Okay, let's suppose a particle follows the trajectory let's go the trajectory y of t equals t squared times some constant. Let's say that constant is a, so that the dimensions work out. So it follows this trajectory a times t squared, where t is time and y is the distance the particle travels. So that's the trajectory that it follows. And a question we might ask, or let's change from y and make it r. So the trajectory it follows, r of t, is equal to a times t squared. Now a question we can ask is, what does this quantity, the derivative, look like for this particle? Well, we can substitute in, so let's start with delta r over delta t, the difference quotient, the ratio between the change in the height to the change in the width. Delta r over delta t is r at t plus delta t minus r at t all over delta t. Substituting the values in, we get that this is as follows. And expanding, we get that this is at squared plus 2at delta t plus a delta t squared minus at squared all over delta t. We notice that at squared and minus at squared cancel. This delta t cancels that delta t and one of those. So this is equal to 2at plus a delta t. Okay, so that's the difference quotient. That's the slope of the line that connects r at t plus delta t and r at t. And the derivative dr by dt is the limit as delta t goes to 0 of delta r over delta t, which is the limit as delta t goes to 0 of 2at plus a delta t. As delta t goes to 0, 2at is a constant. There's no delta t there's no delta t factor in 2at, but the second term has a delta t factor. And as delta t goes to 0, that goes to 0. So this is 2at. So the derivative of r with respect to time, dr by dt, is equal to 2at. This looks very familiar because it in fact is the derivative using the power rule. But there's something more important to consider here. And that's the fact that what we've just found is the speed or the velocity of this particle, the speed of this particle, dr by dt. So the speed of this particle, v, is defined to be the derivative of r with respect to time. The speed here is the magnitude of the velocity. So v equals dr by dt, and that's 2at. So this quantity derivative is very important not only to mathematics, but also describing our physical world. Velocity is the derivative of position. Acceleration is the derivative of velocity. Similarly, many quantities in physics are represented using derivatives. They're derivatives of other quantities. So knowing what the derivative is and how to use it is going to be crucial. Hopefully, this example and this explanation helps. I hope you found that interesting. Like, subscribe, and leave a comment down below. I'll be making more videos like this, so stay tuned for them. Thanks for watching. I'll see you all next time.